Okay, so we have a little bit of a change of pace here. We're looking at some probability, included designated order. And this lesson really has a truth to it, which is that the probability of something happening is really independent of what's happened before. So kind of keep that in mind as we go on. But, one of the basic ideas is that the probability of an event is equal to the number of desired outcomes divided by the total of outcomes in the sample, really the total number of possible outcomes. So let's take a look. First example says a coin is tossed 3 times and is heads each time. What is the probability of heads for the next toss? Well, this kind of gets to the truth of the matter, which is that all of those tosses before do not change the probability of heads coming up this time. So the probability of heads on the latest throw or toss is equal to, well, there's one possibility out of 2. So the probability of getting heads is in fact still 1/2. Let's take a look at another example. You've got 6 green marbles and 8 red marbles in a bag. 1 marble is drawn and then replaced. A second marble is drawn and replaced. Both were red. What is the probability the next marble is red? Well, probability of red, once again, those first 2 little experiments do not affect the outcome, especially considering that the marbles were replaced in the bag. And so all we have to think about is what's happening in this event. Well, in that bag, there are 6 green marbles and 8 red marbles, which means that there's a possibility of getting 8 out of a total of 14 marbles. And we can reduce that down to 4/7. So probability of red is actually 4/7. Now we go to the die. The die is rolled 3 times. The results, 1, 4, and 3. What is the probability the next roll will produce a number greater than 2? Well, the probability of the probability of getting a number that is greater than 2 can be written as probability of n greater than 2. Well, how many outcomes are possible? Well, there's the ones that are bigger than 2 are 3, 4, 5, and 6. So that represents 4 out of a possible 6. And that can be reduced down to 2/3. So the probability of getting a number that's greater than 2 when you roll a die is 2/3. All right, so let's take a look at this one, which adds a little bit of complication to it, but it's the same kind of idea. We have 2 dice rolled, and the question is, what's the probability that the sum of the numbers is 7, a number greater than 8? So there's actually 2 probabilities. So probability of a sum of 7 and the probability of the sum being greater than 8. All right. So what we need to do here is we need to figure out all the possible combinations of sums when we roll 2 dice. So the way that I'm going to track this is that I'm actually going to label all the possibilities for 1 dice here. And then I'm going to do the same up top. And what that's going to allow me to do is to track all the sums. Now, out of the possibilities, let's see, we could get a 1 and a 1, in which case the sum would be 2. We could get a 2 and a 1, which would be 3. 3 and a 1, which would be 4, etc. 2 and a 1 get you 3. 2 and a 2 get you 4. 2 and a 3, 5. 3 and a 1 is 4. 3 and a 2 is 5. 4 and a 1 is 5. 4 and a 2 is 6. 5 and a 1 is 6. 5 and a 2 is 7. 6 and a 1 is 7. 6 and a 2 is 8. Okay, so I'm going to draw a line here just to show a difference between the numbers rolled and the outcomes here. I have a 6 by 6 little rectangle of numbers here, which means that there's 36 outcomes. Now the 7s are right here. There's 1, 2, 3, 4, 5, 6. So which means that the probability of getting a sum of 7 is 6 out of 36, which actually reduces to 1/6. Now the probability that the sum is greater than 8, well, those all live down here, right? Greater than 8. How many of them are there? There's 4 plus 3, which would be 7. So it looks like there's 10 out of 36, which will reduce down to 5/18. Okay, so this next one has a little bit of a compounding component to it. So we can kind of visualize this situation using something called a probability tree. So take a look at this one. If you flip a coin twice, what is the probability of getting a heads on the first toss and a tails on the second? So one of the things that can be useful here, like I said, is something called a probability tree. And the way that the probability tree works is that you kind of track it. So you say, okay, well, what are the possibilities here? Well, on my first flip, I could get a heads or I could get a tails. If I get a heads on the first flip, I can flip it again, and I can get a heads again, or I can get a tails. And if I get a tails, I could get a heads, or I could get another tails. So what this shows us here is that actually there are 4 possibilities. So the probability of getting a heads on the first toss and a tails on the second, well, that's right here, right? Heads on the first, tails on the second. And in fact, that represents a probability of 1/4, because it's 1 out of 4 possibilities. So, fair coin is tossed 4 times. What's the probability the first 2 are heads and the last 2 are tails? Well, we can go ahead and we could actually draw out a larger tree for this. It would be a much larger tree. And what we would find actually is that if we figure out the probability of one event, right, the fair coin, probability that the first one is a heads is actually 1/2. We can multiply that times the probability that the second one is a heads, and then we can multiply that by the probability of the next one being a tails, which is 1/2, and then we can multiply that times the probability of the next one being a tails, right? And so in doing that, what we end up getting is actually the probability of this event happening is 1/16. So again, you can kind of take each of the independent probabilities and you can multiply them together. This is kind of a more mathematical way to jump from the factor tree. You could still draw out the factor tree, but you'd find there's actually 16 possibilities or possible outcomes. One of them is what this is describing. All right, so if you go to the spinner on page 287, the spinner on page 287 kind of looks like this. I can kind of help you out with that. Okay. It says, what is the probability the spinner stops at 4 and then stops at 3? Well, the probability that it stops at 4 is 1 out of 4. The probability that it stops at 3 is also 1 out of 4. So if we multiply each of those independent probabilities together, we end up with a probability of 1/16 that it's actually going to work out exactly as it's described. So take a look at these probability problems, give them a shot, and see how you do.